In this lecture, we will walk through the practical seismic modeling workflow for tall building core wall systems. The goal is to show not just the software steps, but the engineering reasoning behind each modeling decision. This includes stiffness modifiers, mass definition, response spectrum scaling, and interpretation of analysis results. The discussion is based on CSA recommendations and common industry practice for performance-based design of tall buildings. We begin by applying stiffness modifiers based on CSA A23, 3 recommendations and common industry practice. Columns are typically taken as 70% of gross inertia. Cracked shear walls are reduced to about 35%, while uncracked walls may be taken as 70%. Beams are reduced more significantly due to flexural cracking, and slabs are also reduced to represent cracked diaphragm behavior. Next, we initialize the structural model. Instead of using predefined grid lines, CAD drawings are imported directly to define wall, column, and slab geometry. This approach is efficient for complex tall building layouts.
After importing geometry, material properties for concrete and reinforcing steel are defined. Section properties for beams, columns, and shear walls are then assigned, ensuring that stiffness modifiers are consistently applied. Gravity loads are then gathered and assigned to the model. These include superimposed dead loads, snow loads, and live loads for typical floors, as well as higher live loads at ground and basement levels. These loads establish both vertical demand and the seismic mass of the structure. Soil parameters from the geotechnical report are then used to define the site class. Key properties include shear wave velocity, soil density, and Poisson's ratio. These values influence the response spectrum used for seismic analysis. P-delta effects are included to capture second-order behavior due to gravity loads acting on lateral displacements. This is particularly important for tall buildings where drift can significantly amplify moments and axial forces. The mass source is defined from gravity loads, and sufficient vibration modes are generated to capture at least 80% modal mass participation in each principal direction. A response spectrum function is defined based on site class and seismic hazard parameters. The resulting dynamic base shear is then scaled to match the code-required equivalent static base shear to ensure conservative design. Finally, analysis results are reviewed, including story drifts, base shear, and internal forces in the core walls. Special attention is given to coupling beam forces and overturning moments, since these control reinforcement design in coupled wall systems.